8.5 practice problems. The graph opposite shows the titration curve for the aqueous solution of a weak base, B, with hydrochloric acid as a titrant. Based on the graph, which of the following best estimates the pKa for HB+? So our pKa is going to be equal to our pH at halfway before we reach the equivalence point. So we reach equivalence at 50, so our halfway mark is at 25, and then we would just match what our pH is, and that will be equal to our pKa. So our pH looks like it's right around here, just slightly below 11, and so answer choice B is my best choice. The reaction of a weak base, B, with hydrochloric acid is represented in the equation above. The graph above, Q1, shows the titration curve for 25 milliliters of an aqueous solution of B titrated with 0.1 molar hydrochloric acid. Based off of the graph, what is the best, which of the following best estimates the concentration of the weak base? So our volume of HCl added here, we can see that HCl we needed to add 50 milliliters. Since we know that our mole ratio between B and HCl is 1:1, and our equivalence point is where the moles are going to be equal, we can just calculate the number of moles of HCl that was added. And so we have 50 milliliters times the 0.1 molar, and that gives us this many moles of HCl. And the mole of HCl is going to be the same as the mole of our weak base B. And then we just need to find the concentration, so we will divide our number of moles by our volume of the base, which was 25 milliliters, and that gives us a molarity of 0.2, which matches answer choice A. A 40 milliliter sample of a weak base was titrated with 1 molar hydrochloric acid at 25 degrees Celsius. Based on the following titration curve shown opposite, which of the following pairs provides the best estimates for the pKb and Kb for the weak base? So we know that our pKa is equal to our pH at the halfway point, and so we can see that we add a total of 40 milliliters before we reach equivalence. And so at this point, where we are at approximately a pH of 11, and we know that the pH is equal to the pKa, and pOH is going to be equal to 14 minus the pH, or 11, and so that's going to be equal to 3, which will be equal to the pKb. So pKb should be at 3, and the only answer choice that has pKb at 3 is going to be answer choice A, and then we know that the Kb is going to be equal to 10 to the power of the negative pKb. So 10 to the power of negative 3 would be my pKb. So that would be, again, still answer choice A. A solution of a weak monoprotic acid is titrated with a solution of a strong base, KOH. For questions 4 through 6 that follow, choose from the points labeled A through E on the titration curve. The point at which the concentrations of the weak acid and its conjugate base are approximately equal are. And so when we reach our halfway point before the equivalence point, that's when our weak acid and the conjugate base are going to be equal. So that is going to be at point B. Question 5 says the point at which the moles of the added strong base are equal to the moles of the weak acid initially present. That's going to be at the equivalence point, so that's going to be C. And then 6 says the point at which the pH is closest to that of the strong base being added. That is going to be after the equivalence point once I flip over and I am going to be mostly base, and so that is going to be at the equivalence point E. Data collected during the titration of a 20 milliliter sample of a 0.1 molar solution of a monoprotic acid with a solution of sodium hydroxide of unknown concentration are plotted on the graph opposite. Based off of the data, which of the following are the approximate pKa of the acid and the molar concentration of the sodium hydroxide? So we know that the pKa is going to be equal to the pH at approximately halfway. So we know that we are going to be at 10 since our equivalence point is at 20. And then we would just go ahead and see kind of where we are, and it looks like we're just a little bit under 5 there. So that's going to be 4.7 or so. And that gives us just A and B here. Now we need to find the molar concentration of the sodium hydroxide, and we'll do that based off of the fact that our mole amounts need to be the same at the equivalence point. So I know that I added 20 milliliters of sodium hydroxide, and I also had 20 milliliters of the initial sample. Since we are equivolume, we must also be equimolar, and so that would be answer choice B. A 50 milliliter sample of an acid, HA, of unknown molarity is titrated with the pH of the resulting solution is measured with a meter and graphed as a function of volume of 0.1 molar sodium hydroxide added. For some of the questions that follow, choose from points labeled Q through U on the titration curve. At point R in the titration, which of the following species has the highest concentration? So at point R, we are not quite halfway to our equivalence point, and so we are not at the point where we have reached equilibrium. So we definitely don't have as much sodium hydroxide as hydronium, or sorry, as our weak acid there. That would be after we have reached equivalence. We also are not going to be fully equal at the number of my acid and its conjugate base. So here at point R, I am still quite heavily on the acid, not its conjugate base yet. I don't have those at equal points yet. That would be at point S. A student carries out the same titration but uses an indicator instead of a pH meter. If the indicator changes color slightly past the equivalence point, what will the student obtain for the calculated concentration of the acid? So if we were to run this experiment again, but instead of being able to find the pH via a meter, and we were using some sort of indicator that maybe indicated that we had flipped after our equivalence point here, then it would look like we had to have more moles of sodium hydroxide to cancel out the amount of the unknown acid. So our concentration is going to be higher than it ought to be. And so we just need to figure out what the initial concentration or the concentration should have been at when we were equimolar. So at 40 milliliters of 0.01 molar, then that would be this many moles, and we had initially a 50 milliliter sample. So our molarity ought to have been 0.08, but since we indicated that we had reached the equivalence point afterward, we would have had more moles of sodium hydroxide and therefore had a slightly higher molarity, and our molarity that we calculated was at 0.08. So that would be answer choice B. Which of the following is the best particulate representation of the species, other than H2O, that are present in significant concentrations in the solution at point U in the titration? So at point U, we have gone ahead and flipped over. We have a substantial number of hydroxides present, and our acid has dissociated. So we should see none of the undissociated acid. And then we should see both hydroxide and sodium and the conjugate base. So that would be answer choice B. At which point on the titration curve is A negative closest to that of twice that of HA? So when we look at our titration curve here, at S we are approximately equal, and then just slightly after that at point T, before we reach equivalence point, that is where we would have twice the amount of the conjugate base as the initial acid. So that would be point T, or option choice C. An unknown acid is dissolved in 25 milliliters of water and titrated with 0.1 molar sodium hydroxide. The results are shown in the titration curve below. Which of the following could be the unknown acid? So I can see here that the total amount of sodium hydroxide that I added before I reached my equivalence point was 25. And I know that my pKa and pH are going to be the same at my halfway point before my equivalence point. So that would be at approximately 12.5 milliliters of the sodium hydroxide, and then I would just go ahead and kind of sketch a line here to see where I would be, and that gets me just below 4 for my pH, which would be equal to my pKa at that point. So glycolic acid with a pKa of 3.8 makes the most sense for what that acid could potentially be based off of the graph. A 0.35 gram sample of lithium is placed in an Erlenmeyer flask containing 100 milliliters of water at 25 degrees Celsius. A balloon is placed over the mouth of the flask to collect the hydrogen gas as it is released. After all of the lithium has reacted with the water in the solution, the solution in the flask is added to a clean, dry burette used to titrate an aqueous solution of a monoprotic acid. The pH curve of this titration is shown in the diagram above. On the basis of the pH curve, what is the pKa value of the acid closest to? So again, we are going to be looking at our equivalence point. It looks like it's at approximately 25, which means that at halfway between start and equivalence point, so approximately 12.5, my pKa and pH values are going to be the same. And I can just go ahead and sketch a line to see approximately what value that looks like that would be. And it looks like I am between 4 and 6. And so my best answer is going to be B, because again, my pKa and pH are going to be equal at halfway between my start and my equivalence point for the acid. To determine the concentration of sodium hydroxide solution, a student titrated 50 milliliter sample of 0.1 molar hydrochloric acid. The reaction is represented by the equation above. The titration is monitored using a pH meter, and the experimental results are plotted in the graph opposite. At the point R on the pH curve, which of the following ions are present in the reaction mixture at a concentration greater than 0.01 molar? So at point R, I am at my equivalence point here, and so that means that my my acid and base have reached equal concentrations, which does mean that the OH and H have been eliminated there. And I am only going to really be seeing sodium and chlorine present with any meaningful amount of concentration at that particular point at R. The graph opposite shows the titration curve that results in when a sample of 0.1 molar monoprotic acid was titrated with a solution of sodium hydroxide. Based off of the graph, the pKa of the acid is closest to, so I can see that my equivalence point is at approximately 50, and so at 25, that is where my overall pH is going to be equal to my pKa, and then I just go ahead and sketch a line over, and I see that that is approximately 4. Again, pH and pKa are going to be equal when we are halfway between our start and our equivalence point. So since that is 4 for our pKa and pH being the same, answer choice B is going to be my best choice. When a strong acid is titrated with a strong base using phenolphthalein as an indicator, the color changes abruptly at the endpoint of the titration and can be switched back and forth by the addition of only one drop of acid or base. The reason for the abruptness in this color change is that so when we are dealing with phenolphthalein, we are aiming for like a very, very light pink. And so if we are really abruptly going from clear to like a very sharp pink, that does mean that we have a very, very large change in our pH, really close to our end point where we have equimolar between the two solutions. So I'm going to look for something that matches that. A says a larger change in pH occurs near the endpoint of the titration. So that does match. We are experiencing a large pH change, and that's why we would have a large color change. But let's see if there's anything better. B, a buffer solution exists at the endpoint of the titration. That would make the color change not be nearly as dramatic because we would stay at a particular pH for longer. Phenolphthalein is a strong proton donor. That is not the point of phenolphthalein. Phenolphtalein's point is to change color when we reach a certain pH. And it being a strong acid is definitely not why we would ever use it for a titration ever. The pH of the water is very resistant to change. So if my pH doesn't change very much, then my color won't change very much. So no, also we're not talking about the water's pH. We're talking about the overall solution's pH. Phenolphthalein is much more sensitive to the pH of the solution than most other indicators. No. Phenolphthalein is sensitive to pH, but not any specific pH more than any other indicator. It just so happens that the pH is going to be really close to our equivalence point, and we have like a very, very sharp change in pH as to why my phenolphthalein color would be so abrupt to change. A solution performs an acid-base titration and plots the experimental results in the graph opposite. Which of the following statements best explains the experimental findings? So answer choice A says a strong acid was titrated with a strong base. The evidence as evidenced by the equivalence point being where we have a pH of 7. That's going to happen with all acids and bases since we have an equal amount of protons and hydroxides, so no. A strong acid was titrated with a strong base as evidence of the equivalence point being higher than that of pH being greater than 7. Again, no. A weak acid was titrated with a strong base as evidenced by the equivalence point of the pH being greater than 7. So my pH where I'm at my equivalence point does look like we're at approximately 9, which does mean that I have more base than acid, and so I would have more hydroxides present, and to force the overall weak acid to donate its protons. And so answer choice C is going to be my best answer choice. The pH of the solutions for 4 acids prepared at various concentrations were measured and recorded in the table above. The 4 acids in no particular order are chlorous, hydrochloric, lactic, and propanic. If equal volumes of all 4 acids at a concentration of 0.5 molar are each titrated with a strong base, which of the following will require the greatest volume of base to reach an equivalence point? So because all of the acids that are listed here are all monoprotic, we are going to require the same amount of hydroxide to get rid of the hydrogen there. So all of the acids are going to require the same volume of base in order to reach equivalence point, which is answer choice D.